Let's talk about the coefficients of correlation, R, and determination, R squared. Now, back in 9.1, we saw that the coefficient of correlation, that's a measure of the strength of the relationship between two variables. We even drew this picture here that, all right, if here's R always goes between what? -1 and +1. So -1 less than or equal to R, less than or equal to +1. And if we are at 0, that means there's no correlation. Now, we don't have to be exactly at 0. If it's 0.001, there's still such a small number. There's going to be no correlation between these two variables. So if we get far enough from 0, then we're going to claim that there is a correlation. So if R ends up over here, negative correlation, meaning what the line goes down, the regression line goes down. And if R is over here, we're going to say a positive correlation, which means that the regression line would go up. When we're talking about correlation, we have to be very careful that we don't confuse it with causation. So I've got an alert here. Correlation does not imply causation. So let's talk a little bit about these two terms, correlation and causation. So correlation, that's an association between the variables. When one changes in value, the other likely changes in value also. Causation. Now, causation, changes in one variable, those produce changes in the other variable. So I've just rewritten things over here just to get some more room. But here's our question. Why doesn't correlation mean causation? There's two reasons. Here's the first one. There may be an unmeasured third variable that influences both the supposed cause and the supposed effect. Here's an example. Suppose we've collected data on sunburns and ice cream consumption, and we've established that the two are correlated. Now, as the number of people with sunburns increases, the amount of ice cream consumed increases, right? That's what it means to be correlated. As one of them goes up, the other one goes up. But now, that does not mean that the number of people getting sunburned causes the consumption of ice cream to go up. There could be a third. This is called a confounding variable. So a third confounding variable is temperature. High temperatures cause people to stay out in the sun more, and that might cause more people to get sunburns, and also to buy more ice cream. So this third variable is called a confounding variable because it confounds our picture, is actually the cause of both of these other variables increasing. And the second reason that correlation does not mean causation is what is called the directionality problem. So the directionality problem, that occurs when two variables are correlated but also have a causal relationship, but we just don't know which variable causes changes in the other one. For example, we've got a correlation between ice cream consumption and sunburn. So what direction does it go? Does high ice cream consumption cause people to stay out longer in the sun and then get sunburned, or is it the other way around, where does staying out longer in the sun cause people to consume more ice cream? We just don't know which way it goes. Okay, so I guess we've established that the correlation does not mean causation. Now, let's get back to our discussion on these measures, R and R squared. We've already said that the coefficient of correlation, R, is a measure of the strength of the relationship between two variables. And as R gets bigger, as say R goes this way, the relationship gets stronger. And as it comes this way, it's hard to say here. Okay, if it's in here, it's a weak relationship. And as it goes this way, it gets stronger. Now, R squared. Here is a textbook definition of R squared, But we'll read it together, and then I'm telling you, we'll have to interpret it. So just hold on. Let's get through it, and then we'll interpret it with an example. All right, r squared, that's called the coefficient of determination. R is the coefficient of correlation. R squared is the coefficient of determination. And it's a measure of the proportion of the variance in the dependent variable that can be explained by the independent variable. Well, first of all, it is r squared. So r, we have -1 less than or equal to r less than or equal to +1. Now, r squared, if you square everything, is going to be non-negative, so 0 less than or equal to r squared less than or equal to 1. So let's see if we can interpret this r squared. Now, we've got this definition up here, but maybe we can do better with an interpretation. So I'll try it two ways. First, r squared tells us how well the regression model explains the observed data. Now, by model, in mathematics, when we say model, we're talking about an equation. How well does this equation predict? For example, suppose we compute and we get r squared to be 0.80. Well, that r squared equals 0.80 reveals that 80% of the variation in y can be explained by the model. That means we cannot explain the other 20%. So when we put in an x value into our equation, we're not going to get the exact y value back. There's going to be some variation. So why not? Why don't we get the exact value? Well, it could be perhaps that there is a third confounding variable that we have not considered. It could be like that ice cream consumption and sunburn example that we looked at. If I were to put temperature into that equation, maybe I'd get much more accurate results. Here's a second way of looking at this. Now, we just did this example where we said that if r squared was 0.80, that reveals that 80% of the variation in y can be explained by the model. What do we mean by variation in y? Let's try it this way. Let's look at a picture, a scatter diagram. Here's an example scatter diagram. I just made it up. I've drawn a picture here, and I've got, say, r squared equals 0.80. So what does that mean? Well, how about this? When r squared is expressed as a percentage, like 80%, it reveals the percentage of data points that the straight line passes through. That is, r squared tells us the percentage of data points that actually lie on the line. So if r squared is equal to 0.80, that tells us that 80% of the data points lie perfectly on that straight line. I think this interpretation here, where r squared is given a percentage of the data points that actually lie on the straight line, is a little clearer, or actually a lot clearer than I popped it in back here. The definition. So like in this example up here, the data points don't lie exactly on that line. We get some variation. Well, what's that variation due to? I don't know. There's 20%. 20% of the points don't lie on that line. Why not? I don't know. There's some other variable in here, perhaps some confounding variable that's causing the data points to go off the line. And if I knew what that variable was and put it into my equation, maybe I could get those points to line up on the straight line even better than they do now. Let's close down here with an example. I just popped the data that we got off the calculator back in 9.2, the last section. So we got our p-value to be this one right here, right, which is 0.000157, or how about p being 0.0002? So we established there is a correlation. There is a correlation. Now look at our R values, all right? So we get R is equal to 0.9897. Now remember what R does. It measures the strength of the relationship. So here's 0. Here's 1. We're way out here, all right? We're way out there. This is a very strong relationship. And what about this r squared? R squared is 0.979. That tells us that about 97.9% of all the data points lie exactly on this line. And where did that line come from? That came from over here, right on our calculator. It computed a and b for us. And the equation of the line, the model, is y equals a plus bx. Now we have a formula for computing r. We could do it by pencil, but we're not going to do that. We have technology. We live in the 21st century, so we're going to use that technology. Textbooks are going to have us doing this by pencil, making tables. I think we can skip that. So let's just use our technology to get these values. Our concern is, once you get a value, do we know what it means? So with that comment, we'll close this discussion.